6.5 Logarithmic Properties. In chemistry, pH is used as a measure of the acidity or alkalinity of a substance. The pH scale runs from 0 to 14. Substances with a pH less than 7 are considered acidic, and substances with the pH greater than 7 are said to be alkaline. Our bodies, for instance, must maintain a pH close to 7.35 in order for enzymes to work properly. To get a feel for what is acidic and what is alkaline, consider the following pH levels of some common substances: battery acid, stomach acid, orange juice, pure water, human blood, fresh coconut, and sodium hydroxide. To determine whether a solution is acidic or alkaline, we find its pH, which is a measure of the number of active positive hydrogen ions in the solution. The pH is defined by the following formula, where A is the concentration of hydrogen ions in the solution. Using the product rule for logarithms. Recall that the logarithmic and exponential functions undo each other. This means that logarithms have similar properties to exponents. Some important properties of logarithms are given here. First, the following properties are easy to prove. The log base b of 1 equals 0. The log base b of b equals 1. For example, log base 5 of 1 equals 0, since 5 to the 0 power is 1. And the log base 5 of 5 equals 1, since 5 to the 1 power equals 5. Next, we have the inverse property. Log base b of b to the x power equals x, where b raised to the log base b of x power equals x, where x is greater than 0. For example, to evaluate the log of 100, we can rewrite the logarithm as the log base 10 of 10 squared, and then apply the inverse property log base b of b to the x power, which equals x, to get the log base 10 of 10 squared equals 2. To evaluate e raised to the natural log of 7, we can rewrite the logarithm as e raised to the log base e of 7, and then apply the inverse property b raised to the log base b of x equals x to get e raised to the log base e of 7 power equals 7. Finally, we have the one-to-one property. Log base b of m equals log base b of n if and only if m equals n. We can use the one-to-one property to solve the equation log base 3 of 3x and log base 3 of 2x plus 5 for x. Since the bases are the same, we can apply the one-to-one property for setting the arguments equal and solving for x. Set the arguments equal. 3x equals 2x plus 5, subtract 2x, x equals 5. But what about the equation log base 3 of 3x plus log base 3 of 2x plus 5 equals 2? The one-to-one property does not help us in this instance. Before we can solve an equation like this, we need a method for combining terms of the left side of the equation. Recall that we use the product rule of exponents to combine the product of exponents by adding x to the a multiplied by x to the b equals x to the a plus b power. And we have a similar property for logarithms called the product rule for logarithms, which says that the logarithm of a product is equal to a sum of logarithms. Because logs are exponents and we multiply like bases, we can add the exponents. We will use the inverse property to derive the product rule below. Given any real number x and positive real numbers m, n, and b, where b does not equal 1, we will show that the log base b of mn equals the log base b of n plus the log base b of n. The product rule for logarithms. The product rule for logarithms can be used to simplify a logarithm of a product by rewriting it as a sum of individual logarithms. Log base b of mn equals log base b of m plus log base b of n for b greater than 0. How to? Given the logarithm of a product, use the product rule of logarithms to write an equivalent sum of logarithms. 1. Factor the argument completely, expressing each whole number factor as a product of primes. 2. Write the equivalent expression by summing the logarithms of each factor. Using the quotient rule for logarithms, For quotients, we have a similar rule for logarithms. Recall that we use the quotient rule of exponents to combine the quotient of exponents by subtracting x raised to the a over b power equals x raised to the a minus b power. And the quotient rule for logarithms says that the logarithm of a quotient is equal to a difference of logarithms. Just as with the product rule, we can use the inverse property to derive the quotient rule. The quotient rule for logarithms. The quotient rule for logarithms can be used to simplify a logarithm or a quotient by rewriting it as the difference of individual logarithms. Log base b of m over n equals the log base b of m minus the log base b of n. How to? Given the logarithm of a quotient, use the quotient rule of logarithms to write an equivalent difference of logarithms. 1. Express the argument in lowest terms by factoring the numerator and denominator and canceling common terms. 2. Write the equivalent expression by subtracting the logarithm of the denominator from the logarithm of the numerator. 3. Check to see that each term is fully expanded. If not, apply the product rule for logarithms to expand completely. Using the power rule for logarithms, we've explored the product rule and the quotient rule, but how can we take the logarithm of a power such as x squared? Well, one method is as follows. The log base b of x squared equals the log base b of x times x equals log base b of x plus log base b of x equals 2 log base b of x. Notice that we use the product rule for logarithms to find a solution for the example above. By doing so, we have derived the power rule for logarithms, which says that the log of a power is equal to the exponent times the log of the base. Keep in mind that although the input to a logarithm may not be written as a power, we may be able to change it to a power. For example, 100 equals 10 squared, the square root of 3 equals 3 raised to the half power, 1 over e equals e raised to the negative 1 power. The power rule for logarithms. The power rule for logarithms can be used to simplify the logarithm of a power by rewriting it as the product of the exponent times the logarithm of the base. Log base b of m to the nth power equals n log base b of m. How to? Given the logarithm of a power, use the power rule of logarithms to write an equivalent product of a factor and a logarithm. 1. Express the argument as a power if needed. 2. Write the equivalent expression by multiplying the exponent times the logarithm of the base. Expanding logarithmic expressions. Taken together, the product rule, quotient rule, and power rule are often called laws of logs. Sometimes we apply more than one rule in order to simplify an expression. For example, log base b of 6x divided by y equals the log base b of 6 minus log base b of y equals the log base b of 6 plus the log base b of x minus the log base b of y. We can use the power rule to expand logarithmic expressions involving negative and fractional exponents. And here is an alternate proof of the quotient rule for logarithms using the fact that a reciprocal is a negative power. The log base b of a divided by c equals the log base b of ac raised to the negative 1 power equals the log base b of a minus the log base b of c. We can also apply the product rule to express a sum or difference of logarithms as the logarithm of a product. With practice, we can look at logarithmic expression and expand it mentally, writing the final answer. Remember, however, that we can only do this with products, quotients, powers, and roots, and never with addition or subtraction inside the argument of the logarithm. Condensing logarithmic expressions. We can use the rules of logarithms we just learned to condense sums, differences, and products with the same base as a single logarithm. It is important to remember that the logarithms must have the same base to be combined. We will learn later how to change the base of any logarithm before condensing. How to? Given a sum, difference, or product of logarithm with the same base, write an equivalent expression as a single logarithm. So 1. Apply the power property first, identify terms that are products of factors and a logarithm, and rewrite each as the logarithm of a power. 2. Next, apply the product property, rewrite sums of logarithms as the logarithm of a product. And 3, apply the quotient property last, rewrite differences of logarithms as the logarithm of a quotient. Using the change of base formula for logarithms. Most calculators can even calculate only common and natural logs. In order to evaluate logarithms with a base other than 10 or e, we use the change of base formula to rewrite the logarithm as the quotient of logarithms of any other base. When using a calculator, we would change them to common or natural logs. To derive the change of base formula, we use the one-to-one property and power rule for logarithms. Given any positive real numbers, m, b, and n, where n does not equal 1 and b does not equal 1, we show the log base b of m equals the log base n of m over the log base n of b. Let y equal the log base b of m by taking the log base n of both sides of the equation. We arrive at an exponential form, namely b of y equals m. For example, to evaluate the log base 5 of 36 using a calculator, we must first rewrite the expression of a quotient of common or natural logs. We will use the common log. The log base 5 of 36 equals the log of 36 divided by the log of 35. Apply the change of base formula using base 10, which is approximately 2.2266. We use a calculator to evaluate to 4 decimal places. The change of base formula. The change of base formula can be used to evaluate a logarithm with any base. For any positive real numbers, m, b, and n, where n does not equal 1 and b does not equal 1, log base b of m equals the log base of m divided by the log base n of b, and it follows that the change of base formula can be used to rewrite a logarithm with any base as the quotient of common or natural logs. Log base b of m equals the natural log of m divided by the natural log of b, and the log base b of m equals the log base n of m divided by the log base n of b. How to? Given a logarithm with the form log base b of m, use the change of base formula to rewrite it as a quotient of logs with any positive base n where n does not equal 1. 1. Determine the new base n, remembering that the common log of x has base 10, and the natural log of x has base e. 2. Rewrite the log as a quotient using the change of base formula. A. The numerator of the quotient will be a logarithm with base n and argument m. B. The denominator of the quotient will be a logarithm with base n and argument b. Exponential and logarithmic equations. In 1859, an Australian landowner named Thomas Austin released 24 rabbits into the wild for hunting. Because Australia had few predators and ample food, the rabbit population exploded. In fewer than 10 years, the rabbit population numbered in the millions. Uncontrolled population growth, as in the wild rabbits in Australia, can be modeled with exponential functions. Equations resulting from those exponential functions can be solved to analyze and make predictions about exponential growth. In this section, we will learn techniques for solving exponential functions. Using like bases to solve exponential equations. The first technique involves two functions with like bases. Recall that the one-to-one property of exponential functions tells us that for any real numbers b, s, and t, where b is greater than 0, b does not equal 1, and b to the s equals b to the t, if and only if s equals t. In other words, when an exponential equation has the same base on each side, the exponents must be equal. This also applies when the exponents are algebraic expressions. Therefore, we can solve many exponential equations by using the rules of exponents to rewrite each side as a power with the same base. Then we use the fact that exponential functions are one-to-one to set the exponents equal to one another and solve for the unknown. For example, consider the equation 3 of 3 raised to 4 to the x minus 7th power equals 3 raised to the 2x power divided by 3. To solve for x, we use the division property of exponents to rewrite the right side so that both sides have the common base 3. Then we apply the one-to-one property of exponents by setting the exponents equal to one another and solving for x. Using the one-to-one property of exponential functions to solve exponential equations. For any algebraic expressions, s and t, and any positive real number where b does not equal 1, b of s equals b to the t power if and only if s equals t. B to the s power equals b to the t power if and only if s equals t. How to? Given an exponential equation with the form b to the s power equals b to the t power, where s and t are algebraic expressions with an unknown, solve for the unknown. 1. Use the rules of exponents to simplify, if necessary, so that the resulting equation has the form b to the s power equals b to the t power. 2. Use the one-to-one property to set the exponents equal. 3. Solve the resulting equations, s equals t, for the unknown. Rewriting equations so all powers have the same base. Sometimes the common base for an exponential equation is not explicitly shown. In these cases, we simply rewrite the terms in the equation as powers with a common base and solve using the one-to-one property. For example, consider the equation 256 equals 4 raised to the x minus 5 power. We can rewrite both sides of this equation as a power of 2. Then we apply the rules of exponents along with the one-to-one property to solve for x. How to? Given an exponential equation with unlike bases, use the one-to-one property to solve it. 1. Rewrite each side in the equation as a power with a common base. 2. Use the rule of exponents to simplify if necessary so that the resulting equation has the form b raised to the s power equals b raised to the t power. 3. Use the one-to-one property to set the exponents equal. And 4. Solve the resulting equations s equal t for the unknown. Q&A. Do all exponential equations have a solution? If not, how can we tell if there's a solution during the problem-solving process? No. Recall that the range of an exponential function is always positive, while solving the equation may obtain an expression that is undefined. Solving exponential equations using logarithms. Sometimes the term of an exponential equation cannot be written with a common base. In these cases, we solve by taking the logarithm of each side. And recall, since log of a equals log of b is equivalent to a equals b, we may apply logarithms with the same base on both sides of an exponential function. How to? Given an exponential equation in which a common base cannot be found, solve for the unknown. 1. Apply the logarithm of both sides of the equation. A, if one of the terms in the equation has a base 10, use the common logarithm. B, if none of the terms in the equation has a base 10, use the natural logarithm. And 2, use the rules of logarithms to solve for the unknown. Equations containing E. One common type of exponential equations are those with base E. This constant occurs again and again in nature and in mathematics and science and engineering and in finance. And when we have an equation with a base e on either side, we can use the natural logarithm to solve it. How to? Given an equation in the form y equals a e raised to the kt power, solve for t. 1. Divide both sides of the equation by a. 2. Apply the natural logarithm of both sides of the equation. And 3. Divide both sides of the equation by k. Q&A. Does every equation of the form y equals ae raised to the kt power have a solution? No, there is a solution when k does not equal 0 and when y and a are either both 0 or neither 0 and they have the same sign. An example of an equation with this form that has no solution is 2 equals negative 3e raised to the t power. Using the definition of a logarithm to solve logarithmic equations. For any algebraic expression, S, and real numbers b and c, where b is greater than 0 and b does not equal 1, log base b of s equals c if and only if b raised to the c power equals s. Using the one-to-one property of logarithms to solve logarithmic equations, for any algebraic expressions s and t and any positive real numbers b where b does not equal 1, log base b of s equals the log base b of t if and only if s equals t. Note, when solving an equation involving logarithms, always check to see if the answer is correct or if it is an extraneous solution. Access these online resources for additional instruction and practice with exponential logarithmic equations. OpenStacksCollege.org.